Hello, and welcome to the final film in a series of 6 about the standard level equilibrium topic. In this film, we're going to try and bring together some of the things that we've learned about equilibrium and Le Chatelier's principle, along with those things that we covered in the previous film about equilibrium in industry. So hopefully you've seen the other films that go before this one, before you start. What hopefully you'll know by the end of this film is what important chemicals we make using the Haber process and the contact process, and you'll understand the conditions that we use in industry to make these chemicals, not only in terms of collision theory but also in terms of Le Chatelier's principle. So hopefully you'll get a bit of practice deciding what conditions are ideal or what optimum conditions are, those things that we talked about in the previous film. Okay, first of all, let's start off by looking at the Haber process, named after a German chemist who was quite influential in Germany, you could say. He made some of their first chemical weapons, as well as making ammonia on an industrial scale. So the important thing about this process, or the most important thing I suppose, is that it makes ammonia. Ammonia is a really important chemical in making fertilizers, and without it much of the world's population would be starving. Things to notice about this reaction: well, it's reversible, therefore it's an equilibrium process. It's exothermic, we're told here, because the enthalpy change is negative. Okay, and there are fewer moles of gas on the right. There's 4 on the left and there's 2 on the right. So we're going to consider those things when we're looking at what conditions are used when we're making ammonia in industry. Okay, so let's start off by looking at temperature. Remember, we've got an exothermic process, okay? So ideally, we'd like to do this at as low a temperature as possible. So if we have a look at these 5 different lines on the graph, you can see that the percentage of ammonia at equilibrium, in other words, the yield, or how far over to the right we are, is greatest at low temperatures. Okay, so at 200 degrees centigrade, the yield is highest. Why is that? Because the lower the temperature, if you lower the temperature, the system tries to raise it by going in the forward direction, because that's exothermic. Okay, so we'd like to do this at as low a temperature as possible from a yield perspective. But remember that the lower the temperature, the slower the particles are moving, and so the less often they'll collide and the less energy they'll have, so the lower the rate will be. So we might see that we're going to compromise on the temperature. If we look at what sort of pressure we'd like to use, well, remember there are 4 moles of gas on the left and only 2 on the right. So therefore, if we increase the pressure, the system will try to lower it. How will it lower it? By favouring the forward reaction. Why? Because that produces fewer moles of gas. And if you look at these curves, every one of them, as the pressure increases, leads to a higher yield or a higher percentage of ammonia at equilibrium. So you might think, well, we'll use the highest pressure we can. In fact, 600 atmospheres isn't all that high. We can achieve thousands and millions of atmospheres, but the more pressure we use, the more expensive it is. Pressure's good for rate, because the higher the pressure, the more particles there are per unit volume, and the more often they collide. Now, I'm not writing these things down, but they should be explanations that you're pretty familiar with from the things that we've covered, not only in this topic, but also in the kinetics topic. So if we have a look at what we actually do use in the Haber process, here are the conditions that are used, okay? About 200 atmospheres of pressure. So certainly not as high as we can go. So we're going high, but not too high, because we want to save money and we don't want it to go bang and hurt people. What about the temperature? Well, about 450 degrees centigrade. Now you might think that's pretty hot. I wouldn't like to be in a room at that temperature. Remember, this is hot enough to make the rate not too slow, but it's also low enough to make the yield reasonably high. And because we're doing things at a relatively low temperature and pressure, we're also chucking in a catalyst to make things go faster. Remember, catalysts do not affect the position of equilibrium. They have no effect on our yield, but they will make things go faster because they provide an alternative route for the reaction with a lower activation energy. Okay, so be good to remember those conditions for the Haber process, right? Before we move on, okay, an iron catalyst, 400 or 500 degrees centigrade and about 200 atmospheres of pressure. And good also to be able to explain why in terms of Le Chatelier's principle and also in terms of collision theory. Okay, let's have a look now at the contact process. Well, the contact process is, I suppose you could say, it's a sequence of reactions, but the outcome of it is that we're producing sulfuric acid. Sulfuric acid is also quite important in fertilizer manufacture, but it's also very important in lots and lots of other applications, particularly plastics and paints and all sorts of things. But I suppose the important thing for us in this industrial equilibrium context is the fact that the second stage of the contact process is of a reversible reaction, and it has a negative enthalpy change, so that means that the forward reaction is exothermic. Okay, and as far as the moles of gas are concerned, well, we can see we've got 2 moles of gas on the left. Oops, sorry, if we include that one as well, that's 3 moles of gas on the left and 2 moles of gas on the right. So all things that we're going to consider when we decide what sort of conditions would be good. Now let's have a look at what conditions are actually used, and I've got rid of all those other equations because the one that we're interested in is the one that the conditions are used to modify the yield and rate of. Okay, so here's that reversible reaction we saw before. We've got a negative enthalpy change, so exo in the forward direction, more moles of gas on the left. Okay, even though I tried to say there were 2 before, there's actually 3, and there's 2 on the right. So anyway, let's consider what sort of temperature we're going to use. Right, it says here we're using about 400 or 500 degrees again. Why are we doing that? Well, we want to do it at a fairly low temperature because that increases our yield. Why? Because the system will try to increase the temperature by favoring the forward reaction, which is exothermic. Why do we not want to go too low? Well, because that's going to slow the rate down for the same reasons as before. Let's have a look at the pressure that we're going to use. And we can see here that it's only about 1 or 2 atmospheres. Now you might wonder a bit about that, because that's really not very high at all. In fact, it's only just above atmospheric pressure, and you can see that a higher pressure would be good for yield. It would also be good for rate. The thing is that this reaction produces, well, in excess of 90% yield at this temperature and this pressure. So why would we bother spending all that money on pressure if it's not really going to do us all that much good? We're going to chuck a catalyst in, right? We're going to chuck a catalyst in to make sure it goes faster, and it's important to be able to identify this catalyst as well and remember it. So that's vanadium pentoxide, or another name for it is vanadium 5 oxide. Okay, so the pressure that we're using is really just to keep the gases going round. Okay, they're all gases. We want them to go from one place to another, so we've got to pump them somewhere, but we're not deliberately pressurizing this thing because we've got a good yield as it is, and we don't want to spend all our profits on making big thick containers for our reactions. There are some other reactions, as we pointed out earlier, to do with the contact process, and that's kind of shown up here. So it's maybe just worth pointing out the fact that once we make this sulfur trioxide, what do we do to get to the sulfuric acid? Well, strangely enough, you don't just add it to water. If you did, SO3 and H2O do actually make sulfuric acid. The trouble is that's such an exothermic process that as soon as you make it, it just kind of vaporizes, and your factory ends up with just this enormous sulfuric acid cloud in it, which you don't really want. Okay, so what they actually do is they take some sulfuric acid and they dissolve the sulfur trioxide in it. That makes this chemical here, which is called oleum, and then they take that oleum and dissolve it in some more. They dissolve that in water, and that produces 2 sulfuric acids. So although we used some sulfuric acid to start, we got more out at the end. Okay, so what we've done there is we've gone through what we make in the Haber process and in the contact process, and touched on why those things are important, although they're not that important as far as the exams go. And we've also looked more carefully at what conditions are used and why we use those conditions. So we've practiced putting into or considering some of the things that an industrial chemist would consider when they're trying to think about, all right, I want to make this thing go fast, I want to get a high yield, but I don't want to spend too much money and I don't want it to be dangerous. So that's it for the standard level equilibrium topic. Hopefully that film there, which sort of tied a lot of things together, hopefully that made sense. If you've got any questions or comments, as usual, please come and see me as soon as you can, or post a comment on YouTube.